Hi, we're continuing our video series. This one is about using physics to describe projectile motion. So this is where we are. Last time we introduced Newton's laws of motion. Hopefully the following videos will help you to understand Newton's laws of motion better, and specifically how do we use Newton's laws of motion to describe the way our physical world works. So an easy thing to think about is projectile motion. So what we're going to do today is I'm going to introduce you to this concept of something called a free body diagram. And really what a free body diagram is, it's just a way for us to stop and think about a system. It could be a person or a person in an environment. And we just want to start thinking about what are the different forces that are acting on that system or that object. So let's start out, let's think about a person just standing on the ground. Should be simple enough. So a free body diagram, we want to break down what forces are acting on this person. So the person has mass, and we all live on planet Earth. I don't think my YouTube channel has a reach beyond that. So our guy's just on Earth, so he has gravity acting on him. So that is one of the forces. We just want to think about our guy. We'll draw this little bubble around him. So what are the forces that are happening on our guy? So we have gravity. Which way is gravity acting? That is acting downward. So if we revisit Newton's laws, let's look at that first law. If a body is at rest or moving at a constant speed in a straight line, it will remain at rest or keep moving in a straight line at a constant speed unless it is acted upon by a force. So this guy is being acted on by a force known as gravity. So if he's just standing there, why is he not moving? Well, that is where Newton's third law comes into play, this action and reaction. When two bodies interact, they apply forces to one another that are equal in magnitude and opposite in direction. So our guy, even though he has this force of gravity acting on him, he is not accelerating. He's not, in this case, he's just standing there at rest. So that means there's another force acting here, and in this case, it's the ground acting back on our guy. So gravity's acting down, it's causing that guy to put a force on the earth. But the earth is acting back and it's putting a force back on him, and those two forces are equal and opposite in direction. So our guy, the end result is that our guy just stays there. Nothing really all that exciting happens. So let's make something exciting happen. Let's take our guy and let's drop him out of an airplane. So he's dropping out of an airplane. Pretty freaky. He's just free falling through the sky. So he still has that same force. If we draw that bubble around our guy and just think about him as a system or him as an object. So he still has gravity acting downward on him. However, there's no earth in this case to push back on him. So that force of the earth pushing back on our guy doesn't exist in this case. He just has gravity pushing downward on him. So let's think about this in terms of Newton's first law. So a body that is at rest or moving at a constant speed in a straight line, it will remain at rest or keep moving in a straight line at constant speed unless it is acted upon by a force. So our guy in this free fall case, he is actually going to be accelerating. So his speed is going to be changing. He's going to be accelerating downward. That's because he has this net force acting on him, pulling him down. So he's going to keep going down because he is being acted on by this net force. So how do we calculate what that net force is? So what is the force in this case? Well, that's where Newton's second law comes into play. We can actually calculate what that downward force is. So that force in this case is equal to m times a. So m in this case is the mass of our guy, which would be in pounds or kilograms, and then acceleration. So if we want to know the force, we have to know both the mass and the acceleration. So here on Earth, there's a particular acceleration term that is pretty important. That is known as the gravitational constant. So if it's the acceleration due to gravity is equal to this term g. So the gravitational constant has a known value. We can put a number there, and that number is 9.8 meters per second. Now that sounds kind of weird. So meters per second sounds simple enough. So that's our change in position with time. However, acceleration is our change in velocity with time. So if we just looked at these units of meters per second, and we wanted to know if we have a certain velocity that's in meters per second, we want to know how fast that velocity is changing, then we need to do meters per second per second. Hopefully this will make more sense as we go along. So these are good illustrations of Newton's laws. We've actually talked about all three laws here. So one other thing that happens, if you've ever been skydiving, I never have, so I don't quite know how that feels like, but I have been driving in a car at a pretty high speed, always within the speed limit, of course. But I've put my hand outside of the car, and if the car is driving slow, let's say I'm going 5 miles an hour, and I put my hand outside of the car, I don't really feel much. But you think about it, when you're driving along, you probably feel the same thing if you're driving along at a slow speed. However, if you start driving faster, let's say you're going 70 miles an hour and you put your hand outside of the car, what do you feel? You start to feel a force. So what is that force? That is known as wind resistance. It's also known as a drag force. So one thing that happens in the skydiving example, let's do that skydiving example. Our guy jumps out of a plane. He is going to be accelerating downward until he gets to a pretty high speed. But at some point, his speed is actually going to level off. It's going to reach a constant value. So if we did this time and speed, depending on how high he's jumping from, he's going to accelerate, and he's eventually going to reach a constant speed here. That is known as the terminal velocity. And basically what happens with the terminal velocity is you start to get that wind resistance, or that drag force starts pushing back on you. So at first when you jump out of the plane, you're going to be going at a pretty high speed. So actually you have this pretty high wind resistance here pushing back. And eventually, as you accelerate, that wind resistance gets higher and higher. So you're falling down, you're falling pretty fast. This force, this wind resistance force, will keep growing because this force is dependent on the velocity at which you're falling. So eventually, once you get to a high speed at which you're falling, if we're thinking about this in terms of a free body diagram, here we have gravity, and here we have this drag force, also known as wind resistance or air resistance, whatever you want to call it. So what will happen is once our speed levels off, we will no longer be accelerating. We'll reach this constant velocity, and our free body diagram helps us to understand this better. So if we think about what's happening in this case in terms of Newton's laws, so here, in this case where we've reached our terminal velocity and we're no longer accelerating, now we're going to keep moving at a constant speed in a straight line, and we're going to keep doing that unless we're acted on by a force, or really unless the force balance changes in some way. And in this case, we have these two forces acting on us. The gravity force could still be described as, so we'll do F gravity. This is equal to m times g. In this case, once we reach this steady speed where we're no longer accelerating, This is where Newton's third law kicks in, this action and reaction, saying that when two bodies interact, they apply forces to one another that are equal in magnitude and opposite in direction. So in this particular case, the skydiving case, we will no longer be accelerating when these two forces are equal to each other. So really, what ends up happening is Newton's third law helps us do something like called a force balance, where really it's this sum of the forces. So this weird looking E symbol means the summation, or we're adding up all the forces. That is going to be equal to our mass times our acceleration. So this looks a lot like Newton's second law, because it is Newton's second law. But Newton's third law interacts here too, where it's saying if we look at all the forces, the actions, and the reactions, they're all going to add up somehow, and we can put this into a mathematical equation. So in this case, we're going to have our force from gravity minus our drag force. And if we're not accelerating, those are going to equal 0. If they are accelerating, then we can calculate the difference between those two, and we can figure out what our true acceleration term is. So bear with me here. Hopefully you've been introduced to Newton's 3 laws of motion. We're going to start applying these 3 laws of motion, and I hope this starts to sink in as we start to do our own calculations using these actual laws of motion.